Hi, this is Mrs. LaBarbera. This is Physics Chapter 5, Uniform Circular Motion and Universal Gravitation, Video 3. Today's topic is Application of Circular Motion. The objectives are to know that forces causing turning vehicles, planetary orbits, and circular motion of objects on a string. To be able to determine an unknown quantity of circular motion system that involves those three situations, which is turning vehicles, planetary orbits, or objects on motion on a string. So first, let's review Newton's second law. Newton's second law says when the forces are unbalanced, there is acceleration. And acceleration is directly proportional to the net force in the same direction as the net force and inversely proportional to the mass. We can rearrange that equation to get F net equals ma. In this case, F net is the sum of all the forces. It's vector sum. It's also known as the resultant. Newton's second law is used in combination of circular motion equations to analyze a variety of physical situations. Again, please remember that centripetal force is the net force. It's not a single separate force. Steps in solving problems involving forces. Draw a free body diagram. Determine the net force from knowledge of individual forces. Determine acceleration from net force or determine individual force values from knowledge of acceleration. Let's consider case 1, car driven in a circle. In this case, when a car is moving a horizontal circle on a level surface, there is a net force. That net force is centripetal force acting on it to cause it turn. This net force is provided by static friction, which is directed toward the center of the circle. It is static because the car is not moving toward the center. The car is moving around the circle. Let's take a look at the first example. A 2,000 kilogram car travels at a constant speed of 12 meters per second around a circular curve of radius 30 meters. Question A, what is the magnitude of centripetal acceleration of the car as it goes around the curve? Well, equation AC equals V squared over R, straightforward, we get 4.8 meters per second squared. Next, as the car goes around the curve, the centripetal force is directed always toward the center because this is circular motion. Centripetal force, centripetal means center seeking, so toward the center of the curve. The centripetal force of the car is provided by static friction. Again, static because the car is not moving toward the center. D, what is the minimum coefficient of friction that must exist between the truck tires and the road? Let's take a look. In this case, here is a free body diagram. We know static friction is the one provided centripetal force. So we set them equals to each other. Static friction equals to centripetal force. Friction equals to mu s times Fn. In this case, F gravity and Fn are equal to each other. So Fn equals to mg. So mu s times mg equals to Fc. Fc centripetal force is m and m cancels, so mu s equals AC over G. AC is 4.8, G is 9.81, so you will have 0.49. That is coefficient of static friction. Again, coefficient is the number has no unit because it's just a ratio between the two forces, normal force and friction. Another example. Coefficient of static friction acting upon the car is 0.85. So in this case, we're given coefficient of friction. The car is making 180-degree turn around a curve of radius 35 meters. It doesn't really matter what kind of degree it's turning. It's going around a circle with a radius 35 meters. Now determine the maximum speed in which the car can make the turn. So again, this is a free body diagram. Friction, static friction is the one provided centripetal force. So first you write down what is given and you have to know what is unknown, what you have to find. So we know friction is the net force. Friction in this case is providing centripetal force. Friction equals mu times Fn. So this is mu s, 0.85. This is Fn. How did I get Fn? Fn equals to mg, 945 times 9.81. So I get total together 7,880 newtons. Now this friction is the one providing centripetal force. So 7,880 equals to centripetal force is 945 times v squared divided by 35. mv squared over r. From here, you can solve for v is 17.1 meters per second. That's a maximum speed you can turn. If you're over this speed, you will not be traveling in a circle because you will be getting off the circle, sliding sideways. Case 2, a swing bucket. So in a swing bucket, the net force is the combination of gravity and tension. So it depends on the bucket's position. When the bucket is on the top of the circle, the two force, tension force and gravity are pointing in the same direction. So the net force is tension plus gravity. And this net force is the centripetal force equals mv squared over r. On the bottom, the centripetal force is the difference between tension and gravity. It's going upward because it has to go toward the center of the circle. So net force is tension minus Fg. F net equals mv squared over r. Let's take a look at this example. A 1.5 kilogram bucket of water is tied to a rope and whirled in a circle. This is a vertical circle with radius of 1 meter. At the top of the circular loop, the speed of the bucket is 4 meters per second. At the bottom of circular loop, the speed of bucket is 6 meters per second. So it's going faster, it's going slower. Determine the acceleration, net force, and individual force values when the bucket is at the top and the bottom of the loop. Now let's take a look at the top of the loop. We know gravity equals to mg. Acceleration is v squared over r, 60 meters per second squared. F net equals to ma, so we know F net. So we know acceleration F net already. We have to find individual forces. Individual forces is gravity and tension. So the only thing we don't know is tension. At the top, two forces are in the same direction, so F net equals gravity plus tension. Plug everything in. Net is 24, gravity is 14.7, so we can solve for tension equals to 9.3. Similarly, on the bottom, gravity is the same, acceleration is bigger because the bucket is moving at a faster speed. So net force equals to upward because pointing toward the center of the circle. That's 54 newtons up. Now F net is tension minus gravity. Tension minus gravity because tension is up, gravity is down. So we can plug this in, solve for tension. Tension is 68.7 newtons. It's a lot more force, much stronger force on the bottom than on the top. Another example is roller coaster and amusement park physics. So when you do roller coaster ride, you are going loop to loop, right? In a roller coaster, centripetal force is the one provided by the combination of normal force and gravity. So this is kind of like the bucket and the string. At the top, you have two forces add together because they are pointing in the same direction. On the bottom, you have to subtract because the net force is going up, so it's normal force minus gravity give you the net force. Let's take a look at this example. An Litical is riding on a demon at Great America and experienced a downward acceleration of 15.6 meters per second at the top of the loop, and upward acceleration of 26.3 at the bottom of the loop. Use Newton's second law to determine the normal force acting on this 864 kilogram roller coaster car at the top and the bottom of the loop. So here is the top of the loop. Here's a free body diagram. At the top of the loop, we can figure out the net force equals ma. So net force is pointing downward. This because that's the center of the circle. That's a net force. Net force at the top of the loop equals normal force plus gravity because they are both pointing in the same direction. So from there, we can find the normal force is 5,002 newtons. Now here is the free body diagram for bottom of the loop. At the bottom of the loop, the net force is normal force minus gravity. So again, net force equals ma equals to m times a, give you 22,723 newtons going upward. Why is it upward? Upward is the center of this circle. This is at the bottom. So from the net force, we can figure out the normal force. So on the bottom, your normal force is a lot bigger than on top. That is why when you're on the bottom, you feel heavier, because normal force is what you feel, how you feel your weight. And on the top, you feel very light. On the bottom, you feel heavier. This is the reason. That's it for today. Thanks for watching. See you next time.